You're welcome.
I'll let you get started.
Okay, hey everybody, thank you for joining. My session is a little bit different than what the title says. It says sustainability, and we're going to definitely talk about high performance buildings, but the focus is really on loads and how refrigerant systems match loads for high performance systems a little bit better, and then some design considerations when you're using these refrigerant based systems. So just a little bit about us. We're Stephen Winter Associates. We're a design consulting firm. We do all the energy efficiency services for all types of buildings, new and existing. And we have offices in New York, Washington, D.C., Norwalk, and Boston now. I am the director of Passive House Services at Stephen Winter Associates, and I have a team of soon to be about 12, 13 people. We're still growing. And what I'm going to do, when I started here, I was working in the Department of Energy's Applied Research Program, called Building America, and then I transitioned into Passive House. And what I'd like to do with this presentation is show you some studies that we did under that Building America program that shows what the impact of these high performance buildings have on the actual size and calculations that need to be done, or vice versa. So we're going to talk a little bit about residential first. I know most of you are probably large scale MEPs, but we're going to talk about just the first study we did in just low load residential buildings and multifamily, how we actually monitored and calculated equipment sizing in super insulated buildings, and what that means for setback and things like that. And then, you know, what heat pump design considerations you need to think about when you're dealing with these buildings, especially if you're not incorporating energy recovery, and we'll get into that. And then I've got a couple of real-world passive house buildings to show you actual energy demand for heating and cooling on these buildings, to reiterate and to reinforce what I'm going to present at first. And then what do we got to do? What do we need to do going forward? So here's the first DOE study. It was just evaluating the needs for low load buildings on heating and cooling equipment that's available in the marketplace right now. And the most common questions we were getting, this is about mid 2000s, like 2012 to 2015, where we were really getting into high performance design with these Building America buildings. And the most common question we were getting was, what are our recommendations for efficient in-unit HVAC from affordable housing developers that had small energy efficient, small apartments in energy efficient buildings, right? And we were also looking at the beginning of what people were calling the low load homes, and actually coming up with a definition for those. So what the definitions refer to are a building or a home where the design and cooling loads are no greater than about 10 BTUs per hour per foot squared of conditioned floor area. And that was Mark Rosenbaum's initial definition of that in 2010. In a report we read from him. And then Zero Energy Ready Homes, which is the DOE program, was also sort of based on that concept. And so examples of this for different sized dwellings is, so for a 1,200 square foot dwelling, you'd have a design heating level of 12 kBTU per square foot. Per hour. It's not a square foot number. And then for a 2,000 square foot dwelling, you'd have a design heating load of 20, right? So we're under 2 tons for a 2,000 square foot building. And it actually gets way more drastic than that. So what we did was we looked at the availability of equipment out there to serve residential buildings. And as you can see, like most of these units, the individual refrigerant units are much lower capacity than when you get through wall heating and cooling systems. Central furnaces are much larger than we need, way higher than, that 10 kBTU per square foot. And then boilers are even higher. And, packaged terminal units seem to be like they would be more rational, but you have to consider you have to put one in each, if you're talking about an apartment, one in each room that's on an exterior wall. So then you wind up doubling or tripling, or however many rooms you have on that exterior wall that need this 7,000 BTU capacity. And this, remember the time frame of this. So we have some smaller stuff now and some more efficient stuff, but this was just the beginning of our sort of journey through this area. And so we were trying to work with manufacturers to get us small enough equipment. And so we were looking at the market at the time, they didn't feel we had a big enough market. And we were like, yeah, but even a multifamily building just built to code, each of those individual apartments is a low load building. They just don't have the loads that a single family home are going to have. So if you looked at the censuses from back then, and I have a little more current slide I'm going to show you, but dwellings, multifamily dwellings made up 25% of the total housing stock in the United States back then. And then, it accounted for 35% of all new housing starts in 2014. And if you look at this graph, you can see 2014's around here, and it is still going up. We're going to have that dip for the COVID year, but it's going back up again. So the increase in new market starts or new construction starts for multifamily is not going away. They just expect it's going to get larger. And so there is a definite huge demand for low load mechanical equipment. We looked at actual buildings that we've done load calculations for, multifamily units. And you can see like every single one of these is below 1 ton for heating and definitely for cooling. Now, when we start to go to, I know you just sat through Elias's presentation. I heard a lot of people asking about passive house, which is what I do. When you start to get to passive house, you get these bars changing. Cooling becomes dominant, heating becomes the smaller load. And I'll show you, and we'll talk about that in a minute. But you can see the need for these less than 1 ton systems is really high. So one of the DOE findings, we looked at 941 dwelling units in the United States, so single family and multifamily. And what we found was only 1% of the heating and 6% of the cooling equipment capacities were actually right-sized. So they were within 25% or less of the design load, right? So you still even had that buffer. It shows that appropriately sized equipment definitely needs to be developed because we don't have small enough stuff. Over 3/4 of the heating and cooling design loads were less than 1 ton, right? So below 12 kBTU, right? I mean, definitely less than 1 ton. And for attached single family dwellings, over 3/4 of the heating design loads were 25,000 kBTU or less. And that's not passive house level, that's code. So the lowest design loads ranged from 5 to 15 kBTU per hour, and heating and cooling design loads for low load dwellings, even in the cold climate region, are becoming similar in magnitude, which is what I was just talking about with our really high performance buildings. And then the net zero and passive house are pushing this even lower. So here's the results of the DOE study, just showing you heating loads. And the blue dots are what was actually installed, the capacity. And then the red line is what the heating load, design heating load actually is. And so, I mean, obviously, none of these were certainly undersized, and most of them were severely oversized. And you guys know the implications of that. And it's even worse on cooling as far as implications of oversizing, but you can see the same thing for cooling, right? Most of them are drastically oversized. And they said only 6% were within the 25% design of the actual peak load. So what this study concluded was that an all-electric approach to heating and cooling was really the way to go, because we could get smaller sized inverter-driven air source heat pumps that would match the loads more appropriately. The whole house ventilation system was configured for an internal distribution system, right? So minimal ductwork and minimal space conditioning needs. And we definitely needed more low load HVAC options, and that's what is available with refrigerant-based systems typically. So, that was great. That was just standard code analysis. And then we go into passive house. And I don't know if Elias went through the basics of this, but I'm going to do this quickly. It's a building energy standard. That's what passive house is. And just because it has the word house in it, it can be applied to any building type. It's just a concept. It's a very rigorous energy standard. It provides you with caps, so EUIs that you can't go over, right? Energy use intensities or energy demand numbers, depending on what you're gonna refer to in the system. It's holistic in its approach, right? It wants to deal with the envelope first and then reduce mechanical sizing. And then it's really strict on quality control. So we're really concerned about durability of the envelope and comfort. So it's really a comprehensive program. And like I said, the focus is on the envelope and load reductions first and foremost. So we're really driving heating and cooling loads down as far as we possibly can. And you'll see results, a little bit later on in the presentation on that. It's a comfort-driven standard as well, so they want to make sure interior surfaces are no colder than 7.5 degrees compared to the interior air temperature. They don't want you to feel cold, and they don't want that radiative effect. The surface temperatures also cannot be any more drastic than 55 or 132, just for durability reasons. And then the floor temperature restrictions are more restrictive because your feet are in direct contact, and comfort is a bigger issue. The goals are overall building durability, no moisture problems within the building assemblies, no condensation problems on the interior surfaces of the building. Very close attention is paid to those two details. Overall energy reduction, of course, very, very good thermal comfort, also very good indoor air quality. Ventilation is a really, really strong, strict requirement in these buildings. They need to be balanced, high energy or heat recovery ventilation as well. And then obviously carbon emissions, that's what everybody's aiming for, and increased resilience. And I'm going to show you a slide that kind of indicates why passive house buildings or high performance buildings are pretty high in resiliency. This is just a slide showing you all the different types of buildings we're working on, from high-rise affordable in the upper left corner to market rate in the center there. We have some office space on the right in the center of the building there, about 800,000 square feet that is going to passive house. There's an industrial building on the bottom in the center. So like I said, any type of building you can apply the concepts to. And I didn't really finish the thought about passive house, but they give you energy budgets that you can't exceed. They give you one for heating, one for cooling, and one for, excuse me, the whole building. So the designer has some flexibility in there as long as the comfort criteria are maintained. And so you just basically have to stay within these budgets. You just can't exceed them, and that's how you make sure you pass. So another study we did under the Building America program was, well, the passive house software calculates a heating and cooling load for the project. And we wanted to see how they compared to manual J assumptions. So this was our very first passive house project up in Ithaca, New York. It was a community, a co-housing community. And it was made up of a mixture of single family homes with the turquoise and the blue, and then some townhomes. And then this was an apartment dwelling with about 15 apartments, but we didn't wind up doing that one to passive house. The other ones, we all evaluated the other ones. So about, I think it was 7 of the homeowners decided that they wanted to go for certification. And so on 3 of those homes, we wanted to do the testing for the DOE program to see how the actual loads compared to predicted loads, and in both the PHVP and manual J. So the first thing we wanted to do was point out the differences in the manual J assumptions, right, versus the PHVP's assumptions. So they had different outdoor design temperatures. Manual J is based on a 1%, right, design temperature. Passive house uses an average an average daily temperature, 1 for a sunny day, 1 for a cloudy day, right? So this is their cloudy day, this is your sunny day. They also have different interior design temperature set points, relative humidity assumptions, earth temperatures, and then the conditioned square footage is calculated differently for manual J versus passive house. So we wanted to make this clear, like what's different initially in just our assumptions. And so we ran the load calculations using the manual J standard assumptions, and then we entered the passive house parameters. So we had exactly the same areas, set points, everything like that in these parameters. So you can see it's like, 2,500%. So almost a 25% reduction when you just go to the passive house parameters. And then if you look at the passive house, what we also do in passive house to calculate loads is we include solar heat gains, some, not all, and some internal gains from the lights and appliances in the building. And you're going to see why that works. So we monitored 3 buildings, and for 15-minute data over the course of a few months over the winter. And we only took the data from when we went to the ASHRAE design temperature, right? So at 0 degrees, which was the 1% manual J design temperature. And we calculated what the actual loads were compared to the predicted load. So the upper load, the dashed red line, is manual J's load. The lower dashed line is the passive house design load. Green is manual J with the actual interior temperatures of the building. So these building operators kept their temperatures at different. One homeowner kept their temperature at 60 degrees constantly. Another one was at 67, right? So we needed to make sure we were using the same interior design the same interior, the actual interior temperature to compare what the actual loads were. So if you use this for manual J, that's what you get. So it comes down, right? Because we're not heating to 70 degrees anymore, we're heating to something underneath. And then if you look at what the input into the building was, so this is total input. This is all, the buildings are all electric. There's electric heat, electric baseboard, electric domestic hot water. So it's very simple. And the heating was electric resistance. So we didn't have to deal with COPs and refrigerants and stuff like that. So it's a very simple analysis that we got to do. This was the heating system. This was the electrical resistance, right? So that goes on. Those are your manual J's again. So you can see, we're below that passive house design load most of the time with the total input and the heat input. So that was the first building. This is the second building, very similar type of things. You can see your heat input is definitely below our little dashed passive house design load and pretty significantly below manual J. And so I only showed you two graphs. Those were the occupied buildings. The third building we did, house number 3 here, was actually unoccupied. We thought it would be a very interesting comparison because manual J, passive house design loads include some interior loads from the tenants. And so, or some interior loads from appliances and appliance use. And not the tenants in particular, but house 3 didn't have that. They didn't even have any of their appliances hooked up, all right? So they had heat, but they just didn't have their refrigerator running and things like that. And so what you see is house 1 and house 2 with the occupants in it required 25% less energy to keep the space at temperature than the passive house design load. So this was the actual load, and then this was the passive house design load, okay, in this column right here. And so you can see the actual input, the actual load is definitely less than the design load. And for house number 3, they're much closer, right? So the actual load and the design load are very close. And one of the conclusions that we came up with is that it really does indicate that gains from the occupants and plug loads are more significant than anticipated and actually can be used in design calculations, but only for high performance buildings, only for buildings with high performance envelopes. And the reason for this is because they don't respond to that change in temperature of the outside on an hourly basis. They actually only respond on a daily swing. So they're so well insulated and so airtight that they're considered massive buildings, right? So their swings are low and drawn out as opposed to peaks. And so that 0 degree manual J temperature doesn't really apply to a passive house building. It's not going to respond. So all of those internal gains and solar gains actually carry the building as well into the next several hours of cold temperature. So we looked at, as I said, manual J version 8 against the PHPP. So this was a few years ago. I'm not sure what version manual J is at now. And we had 2 different interior temperatures. The internal gains and solar gains are deducted from the total design load in the PHPP, whereas manual J just basically ignores these for design heating load calculations. And on a standard building, I could see that. But as codes get more and more strict and we start to go to stretch codes and net zero codes, we might want to start to look at this. And then it appears that the PHPP assumptions and methods for sizing equipment are far more suited to small single-family homes or townhomes. I do not apply the PHPP sizing calculations to multifamily only because the PHPP does a whole building energy design load. It doesn't do it unit by unit. So you could do it unit by unit, but that's not how we do our modeling for passive house. So we still do, for multifamily buildings, we still do a more traditional calculation method. But the loads are still so low that it doesn't really matter. You can't get equipment that small. So I want to talk about low load homes and setbacks, right? We've been told for years that we should turn back our setbacks at night, save energy, right? Well, you should right size your equipment to make it work better. But if you look at these response curves, right? So we looked at one home, 1,200 square foot in climate zone 6, and we changed the insulation level and the specific heat capacity of the buildings. And the one to the right here shows the recovery time in hours. If you were to lose 4 degrees in that passive house and you had properly sized your equipment, it would take 5.5 hours for you to bring that building back up for 4 degrees, right? So a huge amount of time. Whereas opposed to, and that's at minus 10 degrees outside, as opposed to if you were sort of in an IECC compliant home and you went back 4 degrees, it would take you a couple hours to bring it back up in a right-sized home. And then if you look at, an uninsulated, really old home, you're gonna bring that home back up to compliance with the right size equipment, because this equipment is much, much larger, right? So let's put it in a different way. So if you look at, the design load for our super insulated home, it's only 8,500 BTUs per hour, as opposed to 40,000 in our old home, right? And so look at the lag time, and actually you need extra capacity to bring homes back up to temperature when they're high, have a super high heat capacity. So when you're dealing with super insulated homes, high performance homes, know your client. Is your client somebody that really wants the house to be cool at night? Because even if they want it to be cool, they can turn, a 68-degree home back to 60. They may only drop 2 degrees overnight if they don't open their windows, right? So it's an interesting way. I had a lot of customers who went into a passive house from living in an inefficient home and were like, why won't my house come up to 68 in an hour from 60? And I'm like, because it's not made to do that. It doesn't have the capacity to do that. So it's changing a mindset or sizing a piece of equipment differently. And I really would hesitate to do that, because that's where you get to save all your money in these smaller homes, is on the heating side, or the mechanical equipment sizing side. So, as I said, we were taught size the mechanical systems to the heating load and set back the thermostat at night, and you'll get a lot of energy savings, but it's not true in these high performance buildings. You won't have the extra capacity you need, especially at design conditions. And for setback, the heating system must be oversized if you want to have low setback in low load homes. But again, I still don't think that works, because as long as it takes to increase the temperature, it takes to decrease, right? It doesn't decrease that fast. You're only going to go down a couple of degrees overnight. So know your clients. Okay, so let's talk about heat pumps now, because this is really what we do in most all of our buildings. Now, they can be hydronically heated loops. Refrigerant heated hydronic loops, or refrigerant based loops, that VRF systems. So most of our large scale multifamily projects are going with VRF, right? So you have your one unit on the roof, which is about 6 to 12 tons, and it can feed many, many indoor units. So one of these units could feed about 13 to 16 apartments, depending on how many terminal units they have in the apartments. Have the indoor is just the fan coil unit. So what are your main considerations for this? So how much heat do they provide when it gets really cold, right? You need to make sure you have a cold climate system here. How many are how small are the available terminal units? Some, like a wall hung unit, might only go down to 3/4 of a ton, and your cooling load might be 2,000 BTUs, right? So can you go smaller? The ceiling mounted cassettes can generally go a little bit smaller than that. How much cooling do you get for your glass south facing high internal gains area? So you need to make sure you can meet those areas, because even though passive house responds very, very slowly in heating, it does respond slower in cooling, but the solar gains change that equation. It's a much more drastic change in temperature, in cooling capacity, in cooling with solar gains, than you're ever going to see on the heating side, right? So you need to make sure cooling is going to dominate these projects and the design. What is the efficiency when the temperature drops? And then how much heating cooling do you have? And how much energy does it cost to get it in? So what is the efficiencies of everything? So here's some pros, cons of VRF. The pros, if you have a heat recovery system, right, which is basically the system is set up with the fact that if I'm in an apartment and I want cooling, I can turn cooling on. And if you're in the apartment next to me, but you want heating, you can turn your heating system on. It does not matter how the condenser is set up outside. There's an extra loop of refrigerant typically, and some controller boxes in the hallways that allow the refrigerant to move in different directions. You can recover heat on one and use heat on the other evap, the indoor unit. So heat recovery is very important if you're going to have simultaneous heating and cooling needs in a building. There's fewer pieces of outdoor equipment compared to a mini split system. It is an all-electric solution, and we're constantly trying to electrify our grids, and get off of fossil fuels. We definitely have several cold climate options now, which we didn't many years ago. And then the ratings are very high efficiency. We have very little field data to back it up just yet. We're trying, and I have some thoughts on that. We can talk about that later. The cons, heat recovery costs more. I've heard anything from 15 to 40%. I think it's more in the line of 15%, but it does increase cost of the overall system. And if you're doing an affordable housing project, every bit of money matters in every project, right? But some harder. It's harder to get this in some than others. The smallest unit available, the smallest indoor unit, is probably 4,500 BTU, and we could probably use a 2,000 BTU unit. If you're having to build the tenants for heating or cooling, you need a third-party service because you've got that central condenser up on the roof, and so that adds some complexity and some cost to the building. And then if you don't set it up with heat recovery so that you're saving that money in the heat recovery loop, your system's going to be in either heating or cooling. You don't get to choose. And so October 1st, your building gets changed over to heating, and you're still heating up in your apartment because it's super insulated, airtight, and you're on the south side, and you have 3 people in your house having a party, and you're going up into 85-degree territory, you can't turn your cooling system on. It will not come on. You're only in heating mode. So that is an issue in our airtight, passive house, high-performance buildings. If they only have a heat pump system where they're only one or the other, heating or cooling, we are seeing overheating issues. So this is what they kind of look like. The energy recovery, you can see there's the third loop in there. Instead of just 2 loops, you have all of these different options for the terminal units in the apartment. So it's a really flexible system. So if you have a studio and you just want to put a wall-mounted unit in there, you only need 1 head, that's great. If you have a 3-bedroom apartment, you can do a concealed ducted and just run some short ducts and only have 1 in that apartment. So it's definitely a very flexible design system. Some design considerations. So sizing is important. So if you're going to do wall-mounted systems and you have a 3-bedroom apartment, these wall-mounted systems really only go down to like 4,500 to 6,000 BTUs. And so you're going to have 1 in every room that's on an exterior wall. So automatically you're oversized. Just 1 6,000 is going to probably make you oversized, and then you're going to do 4. So you definitely have massively oversized equipment in your apartment. I'm going to beat this to death. We just don't have it. But you want to make sure that you change the fan settings. So a lot of these come from the factory, that the fan just runs automatically, no matter if it's on or off. You want to change that so that when the unit is not calling for heating or cooling, the fan shuts off, saves energy. You have to understand that the wall-mounted units too are higher to the ceiling where there's warmer temperatures. So higher temperatures are lower heating efficiencies when you're doing heat exchange. Floor or wall fan coil units for heating dominant settings, yes, but we don't have a lot of those in these really high performance buildings. And then most large scale dense projects in North America will be cooling dominated. So in that case, high is okay, because if we need cooling 9 months of the year and heating only 3 months of the year, we're going to be much more efficient in cooling mode. And so you're fine if you have to do it that way. In a high performance building, I'm going to keep giving you that caveat. So here's an actual project that I worked on. It was a historic retrofit project in Climate Zone 5. And what they did was they tried to, each of these purple boxes you see is a zone, right? So they tried to zone each one according to solar orientation, so that if they needed to change one condenser to cooling versus the other to heating, in one wing or the other, they could do that because they did not have energy recovery in the system. So you can't do the simultaneous heating and cooling. The problem is, in these zones, some also included stairs. And the stairs, according to historic, could not be insulated on the interior. And they also had double swing doors, which are very air leaky. And so those zones stay cool as opposed to the apartments. And so if only one zone, say this, say this one zone here needed heating, the refrigerant in this entire zone stays charged in the line. So it's running throughout apartments, and it is enough to keep all of these apartments at least 68 degrees, even if their thermostats are off, if this one zone is calling for heat. And that is like in design conditions. So you really have to make sure that refrigerant puts off so much heat that you have to make sure that zoning according to orientation is important, but also according to load, right? You want to make sure you don't have one room on that is going to be constantly calling for heat, even when it's in the 60s outside because it's cool in there, but the apartments are roasting. So that's really important. And this is explaining that, like, this is 70 degrees. They want this at 70 degrees, but this is running at 74 degrees. So some of the storage units were running at 74 degrees and they weren't calling for heat at all, but they just had no design heat loss. So really be careful about what the set. Oh, and this one is also telling you that the stair was set to 74, but the apartment was only set to 70. So when we first noticed this, obviously we changed these. These all went down into like 60 to 64 range in the stairwells because it doesn't bother anybody to have these lower. But because they were originally set up like this, the whole building was overheating. The corridors were in there 80 degrees. Like it was just a massive confusion of, So the commissioning at the beginning was really crucial. Make sure your cooler spaces are set at a lower set point temperature, as long as they're not occupant spaces, right, where your occupants have to be. The other thing, so when I was talking about even if only one unit on the floor is calling, the refrigerant runs through these systems. So this is a wall-mounted unit and a floor-mounted unit in the same apartment at the Cornell Tech, the house on Roosevelt Island, and our thermostats were off, but the lines were charged for whatever reason. Somebody else on the floor was calling for heat. And you could see that, we're at 97 or 93 degrees almost at this evap, and we're not calling for heat. That's just the heat coming out of it. So they determined in the lab that these floor-mounted units act kind of like a baseboard convector, right? You've got all this heat in the radiator, and then the air is just flowing up over it and is convecting, and it can actually put out 500 BTUs an hour without there any call for heat. So you can understand, like, we walked into this apartment, everything was off. We turned the breakers on. In the evening, we stayed overnight just to see what it was like in these apartments. And it was, I want to say 68 degrees with everything off. It was in the low 40s outside. And when we turned the lights on and we went in and we cooked and these lines got charged with refrigerant because we turned the breaker on, especially this one here. For some reason, this wasn't charged at all until we turned the breaker on. And then by the time we went to bed, it was 75 degrees in there, from 68 to 75, without calling for any heat. And the room I was staying in, which was this one, was up to 79 degrees in the morning. And it was just, you really have to plan for overheating with these systems. You also have to plan for environmental conditions, but I think you guys all know this, right? You don't want these outdoor condenser units getting covered with snow. So the summary of design considerations: if cooling is desired or being provided by the owner, really consider heat recovery. Limit the number of terminal units in each apartment so that you limit the overheating and you save money. And you're not oversized, so the system will run more efficiently. Consider the population that you are putting in the space. Is it affordable market rate? Affordable multifamily? Is it market rate? Is it senior housing? Somebody who want warmer temperatures, cooler temperatures? Really know your market and what type of control they're going to demand from you. And then zone, keeping in mind orientation, space loads, and your set points. You have to make sure you know what's going to happen in all three of those. You'd probably be better off if you have to provide heat to an uninsulated cold space of putting its own heater in there that's not connected to your VRF system. Maybe a mini split, just a 1-to-1, or even just a localized fan coil unit. You got to do the trade-offs there. Okay, so I'm going to run through pretty quickly 2 buildings that we did in Queens, and they're both Passive House certified. They look identical. We call them Beach Green Dunes 1 and 2. They're listed like this because that's what the picture is. This is Beach Green 2 on the left and Beach Green 1 on the right. They're very similar in size. Dunes 2 is a little bit larger and has a few more apartments. And even though they look similar, they've got completely different systems, construction and systems. So 2 is a block and plank building with just exterior rigid insulation and some cavity insulation on the interior. It has ground source heat pumps, central ERVs, and a gas-fired water heater. Beach Green 1 was an insulated concrete form building. Now the R values are similar. I don't know if I have that sheet for you. The efficiencies are similar because they're both passive house projects for the envelope, but that's what the different construction methodology is. They're air source heat pumps, so it's a VRF. It's unitized ERVs in every single apartment. And then this is also gas-fired central recirc, but it has a cogen plant as well. And so just to give you a little input on that, the cogen plant was, the CHP was designed for the domestic hot water demand. About 50% of the domestic hot water is offset by the combined heat and power plant. It provides about 70,000 kilowatt hours. It did in 2020. And then the total gas use for it was about 10,500 therms approximately. The solar array. So each building has a solar array. Beach Green 2 has a larger solar array than Beach Green 1. For some reason, it's not putting out as much energy. So it's still in the commissioning process. We would expect it to be larger than 128 kilowatt hours per year. So we're still working on that. You can see these nice pictures of these solar arrays. I'm missing a picture on here, but Beach Green 2 actually has a carport array on the ground. So they covered some of their parking area. So that's how they were allowed to get, or able to get more. So here's some actual energy use data. Annual site EUI based on their actual utility bills. I mean, look at how close they are. And considering the systems are so different. And really mainly what I want you guys to take home is, look, these are the heating and cooling, demands. Look at how tiny they are. This one, we think cooling might be slightly higher here than we're showing. It was hard for us to parse out the difference between cooling and heating because the ground source heat pump system actually can run in heat recovery mode because it has a water source heat pump in every apartment. And so they can use heating or cooling depending on what they want. So my guess is when we did our regression and did a cutoff temperature, that cutoff temperature was maybe too high for the cooling. It probably should have been lower. So I think we would be more in line with a little bit higher. But still, I mean, look at how tiny these are compared to the overall building EUIs. They're up in the 30s. These are less than 5 and 6% each for those. So once you really focus on the loads, you really, I mean, that's just drastic. That's a massive reduction compared to standard construction. And then if you notice, here's your gas. This is your domestic hot water. Look at what a huge percentage of the building energy use overall that is. Even though these are really good overall, you got to keep that in mind. The whole total is very low. Domestic hot water is still where we can make some really good strides. And then the electric base loads are your pumps, your lights, your plug loads, and there's not a ton we can do with those. So it's just that outlier. So I think the next area of opportunity is when we start to get into our air to water heat pumps or electric heat pump systems for our domestic hot water. We're going to be able to bring that number down drastically. I just want to show you guys a little breakout of like the CHP and the solar here compared to those graphs. Please don't mind, this doesn't really add up to the one on the previous page. That's only because I forgot to take out some of the electrical that is associated with this particular CHP system. So this is the number associated with the actual domestic hot water production. But I just wanted to show you the percentage that was actually CHP compared to the natural gas going directly to the domestic hot water. So very similar again. And then this sort of shows our solar sort of underperforming on this building, but that'll get fixed. But if you look at total electricity, for both buildings, it's very, very similar. And I show these numbers side by side so you can see what the actual numbers are. So heating really comparable, cooling a little bit better. I wouldn't be surprised if the ground source heat pump cooling was more efficient than the air source. I mean, it would make sense. But again, they're so tiny, it's inconsequential. And then our domestic hot water, lighting and plug loads, and then the totals are so close. for like completely different systems. Okay, so what I'm showing you here is the software, what the passive house software predicted versus the actual, so that we can kind of figure out where we're off. And what it comes down to really is domestic hot water. You know, and this is, I mean, yeah, that might be twice, but it's such a tiny portion of the load that who honestly really cares. And then, but this is the big one here, right? So we're off by about 8. So if you added 8 to this 23 predicted, you know, you're really close to what the actual is. And then the lighting and plug loads, we might be off a little bit as far as pumps and elevators and things like that go. We think we need to refine our assumptions for that stuff. I don't think we have enough data to actually figure out that yet, and we're trying to develop research projects so that we can hone in on that energy use and make better assumptions. And so this is for between 2, same thing, you know, look at how close these are. And then domestic hot water again, it's basically the same thing. We're most of the people in our firm kind of agree the domestic hot water use sort of falls between 10 and 15 gallons per person per day, right? That's why we think we're up, because passive house assumes this is a consumption. This is not a gallons per person per day, but the assumption in the passive house software is 6.6, and we think it's more like 12, 13, 14, somewhere in there. So we're about half off, which is actually lining up with this. So here's a chart that shows kind of supports the idea that we need cooling longer. So this was a hourly simulation done to show us if we didn't have heating or cooling, you know, in the building, when do we need cooling in these apartments in a passive house project? And one of these buildings, the lighter line is associated with a north building, and the darker line in both colors is associated with a south building. So you know, they're fairly close, but it shows that cooling is really needed, like almost at the end of March and all the way into the beginning of November. Now, overall, the cooling demands are super low, right? Like you saw that. We're not telling you that you're going to use more cooling in a passive house than you would in a normal construction. We really fine tune the loads, and you're going to see smaller peaks, right? So it's just that you're not losing heat the same as you would in the swing seasons. And so your cooling demand stays up. Your lights and internal gains are really driving the cooling demand in these small apartments. So just something I wanted to point out. And then from a resiliency standpoint, you know, this is your standard sort of peak swing, right? In external temperature, and then what the interior is doing. And then here's your passive house project. You know, it's going to be much lower. The peaks are going to be much lower. And it's going to be offset because we have that lag because of that massive effect that I was talking about. So what this allows people to do is stay in their apartments longer in the cases of outages, in summer or winter, and you know, be more comfortable and not have to worry about freezing and, you know, that whole thing. So definitely a bonus as far as resiliency, and keeping the peaks down helps with grid shift, you know, shifting the peak on the grid loads, and, you know, paying less for energy at off-peak times. There's a lot of benefits to creating this sort of battery of a building, right? It's this energy storage building. So where are we headed? We need work on our turnover of these buildings. They're going to be cooling dominated, but we have to better transition them to the O&M staff. We need to talk to them about it's going to be cooling dominated, and that switching from heating to cooling might be necessary earlier in the year and later in the fall. Passive house windows, you know, they have a limited opening. In all of your multifamily buildings, you're only getting a 4-inch opening. And so when you open a casement or awning window, you get that little bit opening. It's not enough to cool off the space, even in the middle of winter when you've got all of these internal gains. And then, you know, you've got this beautiful airtight building. It's also adding to that lag in heat loss in the swing seasons. So commissioning needs to be an ongoing task for at least the first year or two. It should be that way in any building, but especially passive. If you want to realize the energy efficiency, then you need to make sure that you commission these systems for a couple of years. And then we really have to let the O&M staff and residents know what to expect. You know, you are going to be warmer longer. Open your windows. You can open your windows. It's not bad to open them in a passive house if you're overheating, as long as you're not trying to heat it to 90 and then open your windows. So what we're still trying to figure out is what the actual operating efficiency is of the VRF systems. We just don't have granular enough data. We're constantly looking to get that right now in an existing performance, on an existing performance, not in a laboratory setting. We really have been struggling for years to get our owners to install monitoring data for better analysis, and we're really struggling. We're still struggling. I mean, we've got over 30 projects and completed and on the boards, and like just we can't get enough granular data. And anyone has any suggestions on how you convince somebody to install more monitoring data, I'm happy to listen. And then what's the best or simplest monitoring system for a VRF? And then you need to make sure, you know, what is the optimum level of refrigerant line insulation? If you looked at, go back to that 200 Tyler project, the hallways in there without any heating systems running are running about 4 to 6 degrees warmer than the apartments. So like there's times when there's 74, 75 degrees without any heat being supplied. Now we know our domestic hot water lines run down that corridor. We know our refrigerant lines run down that corridor. So how do we, what is the optimum level to prevent overheating in those spaces? That we don't know. We haven't done that analysis yet. It's not just a matter of, well, you know, do your, you know, thermal analysis of the insulation thickness and the heat loss. It's like line lengths and number of lines and number of apartments and who's going to be running it. And it's a little more complicated than that. So moving forward, we continue to work with the VRF manufacturers to find solutions to this. We constantly let them know what issues we're coming up against and ask them for design advice. We want to increase our education to O&M, and we're working on video content for that for O&M in English and Spanish so that they can rewatch it if they need to, which would be, you know, at a touch of a button in real time. They could just go up and, you know, okay, here's my ERV, what do I need to do? And watch the video. Keep pushing for monitoring, continued outreach to the passive house community at large. And then we're really looking for alternate solutions like high performance packaged terminal heat pumps that are low temperature, and then good, efficient, low temperature hydronic systems where you don't have to run all that refrigerant through the building, and you can just heat the water with air source heat pumps, heat or cool the water with air source heat pumps in a low temperature system, and let the terminal units handle the rest. So that's my spiel. Please let me know if you have any questions. I'm happy to answer any questions.
Okay, Lois, I have a few. Thank you so much. That was a great presentation.
You're welcome.
Let me go in order. Back towards the beginning of your presentation, someone's asking, is the 12,000 BTU per hour for 1,000 square feet criteria for sensible cooling or total cooling?
Oh, good question. No, it's total. We look at, yeah.
Great. Okay. Have you seen applications of passive house or sustainable refrigerant-based heating to a standard school classroom?
With sustainable refrigerant heating to a standard, so like CO2 refrigerant in a classroom setting? No, I have not.
Have you seen passive house for a school before?
Yes, actually. We done a study for the New York School Construction Authority. We're working on one in Massachusetts. Yeah, schools are a big thing for high performance net zero and passive house for sure.
Okay, great. Next is on the example projects you gave, was any consideration given to heat pump domestic hot water systems for these projects? If yes, what drove the choice to use gas?
Yeah, we're trying to do that, and New York's really pushing us to electrify these buildings throughout. The cold climate heat pumps for domestic just don't put out hot enough hot water for reliable cold climate, like really low temp production. You really need to beef up your storage and then have some sort of backup. So most of our clients are really hesitant, but we do have a couple in design that are designing for electrified systems that are not started construction yet, but are in CDs. So the Buildings of Excellence program for New York is pushing for that sort of thing, and we have a couple winners of that program that actually are going for full electrification. And we also have some pilot projects where we're converting existing systems to heat pump systems. Now, on a lower rise system, we're looking at sandons, sort of in stacked in line in I don't know if you call it in series, so that we can beef up the capacity as needed. And then we're also looking at air to water refrigerant systems on a larger scale building to see how they're performing. And so far as I can tell, it's working well so far. But we didn't have that cold of a winter.
Okay, great. Next question is, at what temperature is domestic hot water distributed in multi-unit passive house?
You'll get arguments on this, right? Normally what we see from the engineers is they're looking for somewhere between 140 to 160, and that's in the loop to the tank. But distributed through the building, we try and get 120. That's what we're aiming for.
Okay, great. Next question is, this is maybe a general one that applies to the whole seminar, but is refrigerant heating a good solution for high-rise buildings in NYC? I'll let you take it, but I think we've had a lot of presenters today have shown how it probably is a viable solution, at least.
It is a viable solution. We have a number of projects that are finished. It's just the concerns that people have about, and the people are comfortable. Like I said, these buildings are warm. We don't have any comfort problems that they're too cold. The capacities are no issue. They're super airtight. So the heating demand is being met. People are concerned about refrigerant issues as far as leakage goes and ozone gases, right? Ozone depleting gases. They're worried about occupant safety, and then they're worried about what do we do when we need to replace this refrigerant when it's outlawed, right? So there's all of these other concerns. That's why the low temp hydronic seems to be sneaking in as one of these sort of preferred, let's investigate this some more type of a system.
Next we have, I'm not sure if you would know this, but for large scale multifamily projects, do you experience high volume of heat pump unit maintenance calls?
At the beginning in Cornell, this is where O&M comes in. There was a lot of calls, and it wasn't just the VRF system. It was a combination of getting the comfort rate in the apartments. So what we have at some of these buildings is we have central mechanical ventilation systems, and the air is being tempered before it gets put in the space, and was being only tempered to about 68 degrees. Well, 68 degrees isn't that cold, but when it's blowing on you, it doesn't feel comfortable. So people were thinking their heating systems weren't working. And so there was some back and forth on that. And they were playing with the Evaps, but they didn't know what they were doing. So they were messing up the settings. And then the other thing that they did at that particular building, which they haven't done in any of our other buildings, is they tried to incorporate a really complex control strategy where if a certain percentage of people on this zone were calling for heating, it would switch over to heating. And if a certain percent were calling for cooling, it would switch back over to cooling. And they made it so complicated that it was just switching back and forth constantly. And people were really mad. But it had nothing to do with the refrigerant system. The refrigerant systems work well to provide comfort. We haven't had any problem of them actually performing as far as like providing enough heat. They provide enough heat. It's not a problem.
Okay, great. Those are all the questions I have, unless anyone else has another that they want to ask. That was really good. Thank you, though.
Thank you, guys. I hope it was okay. I hope you weren't expecting something more green. I'm an engineer, so I wanted to do more on loads.
No, I think it was good. I think it's mostly
Okay.
Also. So, okay, well, thank you so much, Lois, and thank you to everyone who attended. That was our last presentation of the day. There's going to be a follow-up survey. The survey is used to get you guys the PDH certification credits that you need. So please fill that out. If you don't see it when you exit the GoToMeeting, you'll be getting a follow-up email from GoToMeeting, so make sure you see that. And I will make these presentations available as soon as I can. We have to edit the video and post them online or whatever. So as soon as we can get that done, we will make sure to get it done.
And I made a couple of edits to the slides compared to the ones I sent you, so I'll send you my latest deck.
Yes, great, thank you. That would be awesome.
Awesome.
Cool. Okay, well, thank you everyone. Thank you for attending and have a great rest of the day.
Thank you.